Hello and welcome to another lecture of power system stability. And in this lecture, we are going to study about Park's transformation. So what is Park's transformation? Actually, Park was a scientist who gave a simplified mathematical model for synchronous machines. And what was actually done in this transformation was that he defined a very new set of stationary variables including current, voltage, flux leakages with the actual winding variables. So we know that every quantity of any particular rotating machine for a three-phase system can be shown by this diagram. So if we see here we can see that there are three phases: phase A, phase B and phase C, and all the three phases are at 120 degree apart from each other. So imagining a particular calculation having three phases at a time becomes very complicated. So what Park decided to define this system with respect to two axes, that is the direct axis and the quadrature axis, that is the D axis and Q axis. D will be for direct and Q will be for quadrature. So now it was a 2D simplified model, and he established a relationship between these three-phase variables into two-axis system of D axis and Q axis. Also, he considered a reference axis as the zero axis. So we can see from this diagram that this figure consists of three mutually coupled coils. First is the three-phase windings, which will be denoted by SA-FA for A phase, SB-FB for B phase and SC-FC for three phase. That makes three in total. Second, we will be seeing one field winding, that is FF dash along the direct axis only. So that is only one number. And we will have two damper windings of direct axis and quadrature axis, which will be denoted by DD dash and QQ dash for direct axis and quadrature axis respectively, thus two in number. So now we will again see that what are the new quantities obtained from this particular transformation. The new quantities available are from the projection of the actual variables on the three axis, which will be along the direct axis of the rotor field, the neutral axis of field winding, that will be the Q axis, and the stationary axis, which will be denoted as D, Q and 0 respectively. So we'll see how it is done. If we represent the MMF of any particular system in a matrix form, then with respect to A, B, C and F, D, Q, we will be having the following matrix as shown here. So if we are denoting it by lambda A will have on the equals this side LAA, LBAB, LAC, then LAF, LAD and LAQ. What are these? These are the self-inductances with respect to A axis only. So A, first term will show how A is related in self-inductance with A. Second, LAB means self-inductance of A with respect to B. Then LAC, self-inductance of A with respect to C. LAF is the self-inductance of A with respect to the field winding. LAD with respect to D axis and LAQ with respect to the Q axis. So this entire line, if we view from this side, as a shortcut you can remember that the first suffix will be the particular variable which we are deciding, that is A, and all the other variables with respect to it on the other suffix side. Similarly, we can do it for B, we can do it for C, we can do it for F, D and Q. Along with this particular matrix, we have a multiplicand matrix of current with it, because we know that lambda is given by the formula lambda is equal to Li. So L matrix we have done. Now we will write the AI matrix with respect to A, B, C, the three axes, then F, D and Q, field, direct and quadrature axis. So A, B, C being the three phases, F for field, D for direct and Q for quadrature. So now we have completed this equation of lambda is equal to L into I. So now the MMF set by coil A along the direct axis, as we know, is given by the formula Km Ia cos theta, which will be along the D axis. Now we have defined that all the three coils are at 120 degree apart from each other. So if this expression is for coil A, coil B will be 120 degree apart from coil A. So if we see in the diagram, we can see here that A phase and B phase are 120 degree apart from each other. So obviously the theta will now become theta minus 120. The only change in this expression from the previous one is that Km remains same, I becomes IB since it is coil B, and cos theta will become cos theta minus 120. Similarly, now if we are talking about the MMF set in coil C, so how it will be? It will be again Km remaining same as in this and this equation. I now becomes IC for coil C, and now this cos you can see is theta minus 240, because the distancing of theta we are calculating with respect to coil A. So again I will just make it clear from this diagram that if you see here the A phase and the C phase here in this particular diagram, you will see that A phase is lagging B phase by 120, whereas now we are talking about the C phase, so it becomes 240, 120, 120, 240. So that is why we are taking now the theta angle as theta minus 240 for C phase. Hope it is clear now. So if we need to calculate the total MMF along the D coil, what it will be for the D axis? The addition of equations, these three equations. So if we are making an addition of these three, as we are making the addition in the form of algebraic addition, so it will include a minus sign in between the thetas, which we have already seen. So this becomes theta minus 120 and theta minus 240. This we have already seen in these two equations. Rest all you can see here that this is your term A of first equation, this for second equation, and this for the third equation. Km was common, so we took it out common, and then we have made the addition of these three. So finally we arrive at the total MMF set up by the coil with this equation. So this was the total MMF set by the coil for the direct axis. It is 3 by 2 Km I D. Similarly, we can do the calculations based on Q axis and 0 axis. I told you 0 will be the reference axis. So we can see here that for direct axis the quantities were in cos, because it follows the cosine axis. Similarly, when we are doing the calculation for Q axis, this cos will now be turned into sine, because it is the sine axis. We also know by the geometry of any figure, if we draw two axes in this form, this axis is the cos axis and this axis is the sine axis. We can just make it that this cos axis is the D axis and sine axis is represented by the Q axis. it will become easier for you. So remember it like this. If there is Q, use sine. If there is D, use cos. So we get the equation of Q just as we got the equation for ID, and 0, that is the reference, will not include any of the terms of cos or sine. Why? Because by again geometry, we know that cos square theta plus sine square theta gives you the result of 1. So we will not include cos or sine in case of I0. It will simply be the addition of IA plus IB plus IC. Okay, so we have got the three currents ID, IQ and I0. If we represent these three equations again in the matrix form, we get a matrix which is similar to this one, this matrix. So what does this matrix say? Referring to the given above equations, we can write it as ID, IQ, I0, the LHS terms, taking 2 by 3 common from these three terms. Here we have 1 by 3. So for making it 1 by 3, what we will do, we'll just see. First we will write the remaining terms, taking cos theta minus 120, cos theta minus 240. Here cos theta minus 120, cos theta minus 240. Right. Then again for the next equation for IQ, we'll take sin theta minus 120 and sin theta minus 240 here. Right. Then again for I0, we have IA, IB, IC, means the coefficient is of 1. So we haven't written anything, but here 2 by 3 was taken outside constant. Here we have 1 by 3. So to adjust it as a multiplicand, we'll just take the coefficients of 1 by 2. So that this 1 by 2 when multiplied by 2 by 3 gives me the coefficient of 1 by 3. Clear? And the coefficients IA, IB, IC from each of the three equations will take as the second multiplicand. So we have written it in the matrix form. Thus we get the equation of D, Q and 0 in terms of IA, IB and IC. So you see how it is easy now for the two variables to be represented in the form of three variables. So this was the simplification technique or mathematical model given by Park. Similarly, you can write down these particular equations for voltage, for lambda and for current. So when we are talking about current, let's take this equation. If I am taking this particular equation, here you will find a term P inverse. What is this P inverse now? You can see this particular equation was represented in the terms of current only. There was no voltage term. But when we are interconverting this particular current with voltage, we need to take the P inverse. So what it is? This P inverse is nothing but the transpose of the matrix taken here. You can see the matrix which was taken over here. This matrix, if I take the transpose of this matrix, I will get what I have here. Just interchange the rows into columns and columns into rows. So we get the P inverse and the relation satisfies itself for this P inverse. So P inverse here also I have mentioned, see in this point, the P inverse is the P transpose, that is the transpose of P, and it is orthogonal, where P is a 3 by 3 matrix. So hope this lecture helps you for all the confusions regarding Park transformation. Looking forward from you for any other requested topic related to this unit or this topic. If you have any suggestions or comments so that we can make the videos more beneficial for you, you can please put it box in the comment box. Please do like, subscribe and comment in the comment section so that we can come with new videos as and when required. Thank you one and all, and hope you will continue your studies in the same momentum. Thank you.